Thanks. So, title slide. All right. Yeah, I'm Andrew Kelley. I am the president and lead software developer of the Zig Software Foundation. And thanks for coming to my talk. So, first thing, where am I pointing here? Pressing the go button.
Not working?
Nope.
We're experiencing technical difficulties.
Oh, okay, I'll press it hard and long.
There we go.
All right. Yeah, just want to tell you a little bit about my backstory. I'm sure it's pretty familiar to a lot of you. I became interested in games at a very young age. And, but my parents gave me a rule that I could only be on the computer or TV or video games for 1 hour a day. It didn't matter what it was, just 1 hour a day. And then I was kicked off. So needless to say, I became very sneaky. My first game was Sonic the Hedgehog 2 for Sega Genesis. So this always has a nostalgic place in my heart. But my favorite games were the ones where you could make your own stuff. Does anyone remember Tony Hawk's Pro Skater 2? They had that level editor, right? That was the shit. Like, this thing was so cool. You can make your own levels. You can put like the start points in there. You can even like make your own gaps, name them, give them points, and then you could like play local multiplayer with your friends and like play horse and tag and stuff. It was super cool. So when I discovered programming, it's like the ultimate game, right? It's like make your own game. That's ultimate power. So yeah, then I got into Visual Basic 6. I still love this so much, right? You open up the program, and then just like any other contemporary program, it gives you a new document, Form 1, just like how it would look. Like, it's just begging you to just drag a button on there and make it do something, right? So, you know, as I progressed, I learned other languages, learned Perl, Python, C++, C, and yeah, I learned them in the wrong order, just like everybody does. And then every time I looked at my own code, even from just like a week ago, I would always think it looked like garbage. I'd be like, yeah, that code I wrote a week ago, it's trash. I've learned so much in 1 week, right? That was my experience for like 10 years. You know, every time I looked at my old code, I was like, I know how I can do it better. But then it stopped, right? After, you know, about 10 years of experience, I'd start to write code, and then I go back and look at my old code, and I think, yeah, you know, fair enough. Like, if I did it now, I'd just do it pretty much the same way. Like, I don't really see any improvements I can make. So, and you know, part of that whole process was, you know, learning like, oh, object-oriented programming that they teach us, not quite right. Like, you know, you learn your own way to go, you know, but I still plateaued, right? At some point I hit this plateau. And, but then something happened where it started happening again. And I'm in this phase right now where I'm looking at code I wrote 4 months ago, and I'm seeing problems again. I got past the plateau. And for me, that was learning about data-oriented programming. So to get here, you know, I watched a bunch of talks on YouTube. That's a pretty famous one. In fact, let me just take a little moment here. I think if I'm going to do a talk on data-oriented design, I think I better... Yeah, that feels right. Yeah, it feels right. Okay. Anyway, so yeah, in order to get here, I watched some talks. You know, I attended Handmade Seattle 3 times. You know, talked to a bunch of people, and then I read this data-oriented design book by Richard Fabian. But it still took me a long time to get it. Like, it just didn't click for a long time for me. So my goal of this talk is that if you're here, if you're where I was for this 10-year period of my life, I want to help you like get over it with me. Like if you have the same like learning model as me, maybe I can like help you just like fast forward, right? Okay, so let's do this. What's a computer, right? The big picture. If I run LS CPU on this laptop that I'm presenting with, oh wait a minute, we're doing it totally different than I thought. Just kidding. If we run LS CPU on my main laptop, it tells us a little bit about it. So 8 cores with hyperthreading. I got this amount of L1 cache, L2 cache, L3 cache, What does that mean? So here it is in kind of like graph form. So this is high level. What the hell is a computer from the perspective of memory, right? And if you notice, L1 has a very small amount of memory. L2 has a little bit more. L3 has a little bit more. And then main memory is huge, right? So there's trade-offs here. L1's real fast. L2's a little slower. L3 is a little slower. And main memory is a lot slower. So just try to keep that picture in your head when I go on to this next slide here. So we have, thanks to ithare.com for this chart. And if you later, just go look up this chart because it's super interesting. And I'm only going to highlight a couple points here. But what I want to point out is where those L1, L2, and L3 are on this chart, right? And if you look over, sorry, wrong button. Ooh, this one. So if you look over here, every time we go down, it's an order of magnitude, right? L1, really fast, okay? L2, order of magnitude. L3, order of magnitude. Main RAM, order of magnitude, right? And the other interesting point is that all this stuff, there's so many things that a CPU can do that's way faster than reading from main memory, right? So like in particular, notice that the fastest thing you can do is math. Like math is faster than reading from memory. So you can draw a pretty interesting conclusion from this, which is like, should you memwise results of doing math? Maybe not. You might actually just be slowing yourself down by not repeating the math, right? And that includes multiplication, right? Multiplication's right there. Faster than L1 read, even, right? And then furthermore, since we're focusing on memory here, I want to highlight one more thing. So kernel call is one of the slowest possible things on here. And that's something that might happen if you call malloc, right? If you heap allocate. And just to highlight the talk on the JSON parser, that correlates, right? Because they found out in the first round, it was malloc doing kernel calls that was taking the performance down to this order of magnitude, right? Okay, so what's the takeaway here, right? The CPU is fast, but main memory is slow. So, okay, now we understand, but how do we apply that? Like, what do we actually need to do? So we need to do more stuff on the CPU. We need to do less stuff with memory. We'll drill down into that more. But let me just one more big picture mental model help you out with this. So try to think of it like whenever you need to do any memory access, you're always going to go through a cache line, always. So the question is, are we going to have to evict a cache line in order to do the job? So let's say that I'm storing something to memory. Each cache line is typically about 64 bytes. Could be 32, could be 128. It's usually 64. And that's the granularity that you have. So if you're going to access something from this part of a 64-byte chunk, and then you want to access something from the same 64-byte chunk, that's good. You're not going to evict a cache line. But if you access something really far away, you might require another cache line to get involved. You're going to increase the chances that you evict one, right? And so the whole point here is just don't have cache misses. That's the whole point, right? So now I'm going to make this, so my talk title is Applying Data-Oriented Design in practice, right? I want to help you do it like, we all know we want stuff to go faster. We want high quality code. What do we actually do? So here's one strategy you can use among many that you can use to apply data-oriented design. Okay, think of your pet project. Think of the thing you're working on. Think about where you have a lot of objects in memory of the same kind, like a struct. Think about a struct that you have the most of in memory. And think about how you can make it smaller. That's the whole trick. That's all we're going to talk about today. So, part 2. I'm going to do like a short lecture on how structs are laid out in memory. And this part's interactive, so I want people to like shout out. Don't feel like you can be a smarty pants know-it-all. Don't worry, just go for it. So every type in programming, like C, Zig, Nim, whatever, It has a natural alignment and a size. And let's just go with some examples. We'll do example-based learning here. So U32, right? 32-byte integer. What is the natural alignment? 4. Good. And the size? 4. Okay, good. Everyone's on the same page. So let's go a little different. All right, a bool. Natural alignment is? And size is? All right, I heard some different answers. So alignment's actually 1. You can just load a bool even if it's not aligned, you can just load a 1 byte, no problem. Alignment 1, size 1. All right, next challenge. A union with a U32 and a bool. Natural alignment is? 4. I'm hearing 4s. And size is? All right, I'm hearing all correct answers. Yeah. Okay. Now, instead of a union, let's go struct. Natural alignment is? Ooh, I'm hearing some different answers. Size is? I'm hearing 8. So the alignment is the alignment of the biggest one, which is the U32. And the size is, here's how it works. You start with each field, and you add the size. So we go from 0 to 4, okay? And we put the bool right there. So now we're at 5. But now we're at the end, so we have to go to the struct's alignment. So we have to add 3 more bytes, boom, 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 to get back to 4. So the answer ends up being 8. Okay? All right, let's keep going. Now we have a struct. We have a U32, U64, U32. What's the alignment? 8's right. And the size? Yeah, you had to do math on that one. Yeah, 24, right? Because the algorithm is start at 0, we go 4, but then we have to go aligned, so we have to go up to 8. And then we put the 8 one in there, we get 16. And then we put the 4 one in there, we get to 20. But now we're not aligned yet. We have to go 4 more to get back to 8 alignment. So now we're at 24. So just by moving these 2 fields around, right, we put the 2 ints in a row. Now what are we looking at? What's the alignment? Same alignment. And the size? Yeah, we went back down to 16. Now, maybe your language is going to do this for you. You know, some languages do. But that's not my point. My point is, on the computer, this is how it's going to work. Like, if the language does it for you, great. But this is what the language is doing for you, right? Okay, I have one more. Let's put another bool on there. Now where are we at? Alignment's the same, right? 8. How about the size? Ooh, I heard different numbers. Okay, we're back up to 24. Yeah. So this is wild, right? Because a bool is like in information theory, a bool is 1 bit of information. But we went from 16 to 24, right? We paid the cost of 64 bits just to add 1 to the struct. And I remember from Mike Acton's talk on data-oriented design, he was so mad about this Boolean that was in a struct in like Ogre 3D or something, right? I remember watching this and thinking, yeah, he was so mad, and he did this like script that like printed out how many bits were being wasted or something. And I was like, okay, I get it, but like, the hell am I supposed to put that state? Because I need to know if it's true or false. Like, what am I supposed to do, right? So I'm going to try to answer that question. And so here we go into the next section here. So here are some strategies that you can use in practice to take a struct and represent the same information according to information theory. You're not losing any bits, but you're reducing the footprint in memory of your struct, right? So let's look at, we'll get back to the bool one in a minute, but here's another example. Here's a struct with some pointers, okay? So if we're running on a 64-bit CPU, we're looking at 32 bytes, right? If we're running on a 32-bit CPU, we're actually only looking at 16 bytes. So, interesting observation, even though 64-bit computers can, have more RAM, by default, they actually also use more RAM, right? Because each pointer is double the size. But there's something you can do. Just use integers. So if we don't heap allocate these objects, if we have them in an array list, for example, and we use indexes instead of pointers to refer to them, we've halved the size of the struct on 64-bit CPUs. So use indexes instead of pointers. That's a trick you can use to have a smaller memory footprint. Now, I have to say, oh, sorry, I want to make one more point too. We also reduced the alignment, right? The alignment went from 8 to 4 in this case. So if you wanted to add just a 32-bit integer in a fifth field, you're not wasting anything, right? Because if we tried to add a U32 onto the other struct, we'd be paying for 4 bytes of padding. Here, it's 4-byte alignment. We're not going to pay for that 4 bytes of padding. So that's another benefit. Okay, but I have a warning, which is watch out for type safety, because in the pointer example, you're going to get compile errors if you use the wrong type of stuff, right? You pass an A and you should have passed a B, compile error. If they're all integers with no types, this is, you've made debugging harder, and you've made some possibly interesting bugs possible, right? So you have to watch out for that. Maybe your language has distinct integers. That will probably help. Zig doesn't have them. Maybe we should add them. I think Odin has them. There you go. Use Odin for this use case. I also would say, if you write this down, go search the internet for handles are the better pointers. There's this blog post by Flow of Woe, Andre Weisflog. It's really good. And so I'm just telling you, like, here's something you can do. I'm not telling you the details of, like, here's how you use integers instead of pointers. This blog post will tell you, here's how you use integers instead of pointers, right? It's the how instead of the, like, what, right? Okay, so there's that one. We took a, what was our original size? 32 bytes. We got down to 16 with this example. Okay, what else? Okay, here's an example. We're going back to that Boolean, right? So we have a pointer, we have two 32-bit ints, and we have that bool. So if we look at the size of this, we're looking at 24 bytes, right? This is the same example. 24 bytes on 64-bit CPUs, 16 bytes on 32-bit CPUs. Lots of wasted bits. I did a little bit of math here so you can kind of get a feel for it. If you had 100 of these, that'd be 2.4 kilobytes. So this is where I was thinking, like, what can we do? I need to know if the monster's alive. Like, I can't just delete that field because I have to know what the answer is, right? So the trick is you can store that information somewhere else. So by having 2 arrays instead of 1, you have all the alive monsters in one array, all the dead monsters in another array. Now that Boolean, that according to information theory, it's still there. It's which array is it in, right? But according to your memory footprint, it's gone. So we went from 24 on 64-bit CPUs to 16, right? And if we do the other trick that I just mentioned and go to indexes, we're down to 12. So here we go. This is another trick. We went half, right? We were at 24. Now we're down to 12. Instead of taking up 2.4 kilobytes for 100 monsters, we're taking up 1.2 for 100 monsters. There's another benefit to this too, which is that if you had a loop where the first thing you're doing in the loop is saying, like, if the monster is dead, skip them, right? Which you can imagine you would do in your game. Now you're just looping over only the alive monsters. And before, in memory, you were touching that flag, right? You were doing a memory load of alive to see if they were alive, right? That could evict a cache line. But if we only look at the alive monsters, we're not paying for that check. There's no branch, there's no load, and that's gonna result in less cache misses. So store Booleans out of band. That's the answer to the question, the part that I did not understand when I first watched Mike Acton's talk. Okay, here's another one. I'll give you a second to kind of study the struct layout here. We're gonna go with the monster, but I'm just gonna keep swapping out the fields to just different ideas. So again, we have a pointer. Now we have an enum that tells what kind of monster it is. So we got 5 monsters here, or 5 animals here. And yes, humans are monsters. So in this example, I did 10,000 monsters, and I did a little calculation, 160 kilobytes for all this stuff, right? So let's look at how this is laid out in memory. In memory, we're going to have, this is called array of structs, right? So at element 0, we have all the fields of the struct. And then before we get to element 1, we need element 1 to be aligned. So we had to insert 7 bytes of padding to get back to 8-byte alignment. so that the struct, so that element 1 could be properly aligned. And then same thing for element 2. At the end, we had to have more padding so that element 2 can be properly aligned. So every single element is paying 7 bytes of padding. But there's a really simple trick you can do. Instead of having one array where you have the struct as the element, you just have multiple arrays with each field as the element. So this is called struct of arrays. So if your programming language lets you use a multi-array list, for example, that's a 5-character fix. Same API. And now the elements are right after each other, right? We have the pointer, 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 pointer. Those are all 8 bytes aligned. No padding needed. Then we have enum, 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 enum. Those are all 1 byte. Remember, 1 byte things don't need any alignment. So we just eliminated the padding by putting them in different arrays. So if we go back to our example, this is the 1-line fix. We just used a different data structure. And now we went from 160 kilobytes for 10,000 monsters to 91 kilobytes, right? That's no joke. That's a big savings, just by limiting the padding. So eliminate padding with struct of arrays. That's the trick. What else can we do? All right, here's another one. So in this case, we got a monster, we got some HP, some XY coordinates, we have an array of them. Okay, now we have this thing where each monster can have like 4 things that they're holding. Maybe we use 0 for empty or something like that. So I ran the script, I ran the calculation. So if there was 10,000 monsters, this would be 366 kilobytes, including the array list capacity overhead, right? The part where you overallocate all that stuff. And that'll become clear why we're now including that calculation in a moment. Let's say that we make a hypothetical observation. So let's say that for our use case, we just happen to notice that 90% of monsters are not holding anything. All of their items held are empty. So if we make this observation, we can exploit it. So now we take out that field and we just store that out of band. Kind of the same thing we did with the Boolean, right? But now we're using a table. So as long as we can use a index for the monster, and that's the key of the hash map, we can just put that data as the value, and now it's sparse. And if we do the math, and I did a whole bunch of scripts to calculate these numbers. There'll be links. There'll be like a gist link, the slides at the end, so you can check my work if you want. Just go download it later. You can play with it. But anyway, so I did the math. With 10,000 monsters, we went from 366 to 198 kilobytes, including the overhead from these data structures, right? The savings are there. And that's with only 10% of monsters holding something. And I also want to point out, like, we could have done different things. Maybe it's that most monsters are only holding one thing. So then you would put that in the struct, and then you'd have the special cases for when they're holding like 4. You can really choose to store the data according to what makes sense heuristically for your observed experience. Okay, so store sparse data in hash maps. That's that one. I got one more for you. And this is kind of the cool thing I'm bringing to the table here. So please take the time to understand this a little bit, because I think this is kind of like one of the cool things that I've done. So I won't make you do too much hard stuff, but this one's interesting, right? So I'm going to give you 15 seconds to shout out how many bytes is this struct. We got 28. Any other guesses? I'll tell you that's not it. You might be forgetting that the union is tagged. I heard a 32. Okay, that's right. So the human struct is 20. The bee struct is 1. There's a tagged union there. So there's a tag, right? That's just an enum. And then there's the payload. So 32 bytes. Now, this is using a strategy where we use the same size for every monster, right? If we could put these all in an array, and each element would take up 32 bytes exactly. That has convenient properties. But we are paying, if we have a lot of bees, we're paying for all those humans, even for the humans that are not bees. It's a funny sentence. That's true. Okay, so let's check a different strategy. Let's try organizing our data a different way. So Here, I've actually taken an object-oriented approach, or I guess you could just call it polymorphism. To me, those two things mean kind of the same thing. But we've reorganized the data so that there's a base struct, okay, that's tag X and Y, and then each specialization of it just adds stuff. So the bee adds color, and the humans add hat, shoes, shirt, pants, and hats, braces, right? This is actually an improvement. So if we do this, we're looking at 24 down from 32, right? This is an improvement. We have used less memory. In terms of how much memory is used for a set of objects, we have reduced the memory footprint through an object-oriented approach, right? But can we do better? So take special note right now of all the state that we need to represent, because on the next slide, it's less obvious how all the state is represented, but that is the point, right? So maybe a focus on, like has braces, for example, will be interesting. And maybe like the color of the bee, right? Yellow, black, red. So here we go. So this is what I call the encoding approach. And in this example, there is a tag, and there is some common data, but we get back to the property that they all, there's a common amount of data that takes the same size, and then there's sparse data stored externally. We're kind of putting all of the lessons together for this one. So you can see that bees, there's no longer an enum for bees. The color for bees is now extracted into the encoding tags. Likewise, we have 4 encodings for humans. So we've chosen to represent naked humans differently than clothed humans, and we've chosen to represent humans with braces differently than humans without braces. So that has braces has disappeared into the encoding tag. The bee color has disappeared into the encoding tag. You can see how we're kind of, the out-of-band theme is coming back, right? And so how this works for humans, let's look at human clothed. Like, how do we know all the information for human clothed? So in this case, the monster is a struct of arrays, multi-array list, right? So we're not paying for padding between the tag and the common struct. For a clothed human, we're going to repurpose the, oh, I don't need a pointer, I did it in the thing. There we go. So the extra index can be repurposed depending on the tag. So if the tag is human braces clothed or human clothed, we know we have to look at the extra index field and then go look up this struct inside this extra thing. So that's how this works. And then let's figure out the size. So if you want to encode a B is 13 bytes because you need the tag, the common struct, but that's it. The color, we could have put the color here, but we didn't even use this. We just put the color here. So we even have extra data about the B we could store. This is not a fully loaded, fully efficient data structure. This is not optimized for memory footprint. This is optimized for fitting on the slide. Like, let's be honest, right? So here's what this comes out to. Now, in order to give you a number, I have to add more assumptions, right? Because we made how much size stuff takes depend on the actual thing that you have in practice. So we have to make some assumptions in order to report how did we do, right? Which is good because what we're learning is that by taking in the heuristic information about your actual data, you can create encodings that work better for you. So here we have to assume equal distribution of humans and bees, and we have to assume some kind of distribution of naked and clothed humans. And I feel like a realistic distribution of naked and clothed humans is like half and half. I feel like that matches the world. So let's do that. That comes out to 17 bytes per monster. So we went down from 32 to 17. Almost broke that in half again by switching to an encoding approach. And yeah, I think I made this point already, but choose encodings according to your actual distributions, right? If half and half naked and clothed is not what you have, pick something else. Like maybe most humans are just walking around with a hat and nothing else, in which case you would want a human with hat encoded, and then you could just put the hat as the extra index, and then you got 13 bytes for humans with hats. Done, right? Okay, so that's the encoding approach, and we're going to come back to that in the next sections of the talk. So that's the 5 lessons. That's the 5 strategies that I want to share with you, and that's it. That's the take-home knowledge. But I do have a case study. So I did these things in the Zig compiler, and I just want to report my findings so that you know. This is not just me, at home, just like, oh, maybe I can move the data around. I tried it for real in a real project, and I will share with you the results. But I will say, this guy's pretty cute, but since we're talking about performance, gotta go fast. So this is the pipeline of the Zig compiler. If it's pretty standard. On the very left-hand side, we have source code, which is what you type into the editor. Right-hand side, we have machine code, which is what the CPU understands. This stuff is logic. So this is like implementations of doing stuff. This stuff is data, right? Source code is data, machine code is data. But we can't control what the source code format is or what the machine code format is. Machine code is specified by the hardware. The source code is specified by the language specification. But everything else, that's compiler details. We can just pick whatever data we want, whatever data layout we want for this. So all those principles that I just talked about, we can apply them here. That's the core pipeline of the compiler. So if this stuff actually works, we would expect to see good results, right? I also just want to take advantage of the fact that I'm bothering to document this stuff just to explain that everything to the left of this line is done on a per file basis. Doesn't matter what flags you pass, doesn't matter anything. Like what the same source code results in the same ZIR data. And on the right-hand side of that, we start to have to get more involved in the compiler stuff. It's per function. And when we start to get into code generation, now we have to do something different for ARM, the x86. You get the idea. I also want to foreshadow that this part here is embarrassingly parallel. So we'll come back to that point. And let's hone in on the tokens. So let's go look at how we can apply these memory footprint reduction strategies to a real-world project where our goal is to tokenize source code and output a list of tokens that can then be used to parse for a compiler. So I'm going to throw a struct at you here. I'll go. Now we're not doing exercises, so don't feel bad if you didn't get it exactly. I'm not going to ask you to try and calculate these. This is more high level at this point, but I'm just kind of reporting. So this is how it used to be, right? It used to be that you might recognize this, right? This is the tagged union approach where everything's the same size. You can see that I got an enum there. There's some padding, right? This is me right now looking at my old code and being like, oh, now I see the mistakes again, right? So there's the enum. Is there a Boolean here? Probably. Why are we using 64-bit sizes? Why are we storing the line and column? We can just calculate those. I'm almost delighted with how bad my old code looks to me again, finally, right? So yeah, to say it more succinctly, we can compute line and column lazily, get them out of there. Another point, let's make a reasonable limitation. We only want to be able to compile 4 GB source files or smaller. If we make this limitation, we can make a better, faster compiler. So let's use smaller amounts of memory to store those. Okay, other point. Do we need to store the end position of a token in a compiler? I mean, we can just re-tokenize it again, right? We can just do a little bit of math again and avoid storing some memory. Also, in the compilers, tokens are just asterisk, slash, or the and keyword. We don't even need to retokenize those. We just know the end position based on the fact that it's the and keyword. It's obviously 3, right? Finally, why are we parsing integer literals? Why are we parsing string literals during the tokenizing? We can just do that later. It'll be the same cost, but now we can make our tokens way smaller by not storing all this extra data. And then, yeah, so here's the results, right? I went through all my own strategies, took my own lessons, and we went down from 64 bytes per token to 5. It's just, it's just where is it in the file and what is it that's right there in the file. That is what a zig token is now. So yeah, it's much smaller. And we have a lot of tokens, right? You can imagine, every identifier in your source code, every asterisk, every slash, that's a token. So every single one of those is taking up 5 bytes instead of 64 when the compiler is doing its work. So that's that one. We're going to look at AST next, and then I'll show you a benchmark, and then we'll go to the next one. So, okay, AST, I'm going to show you another struct again. So this is how it used to be. Actually, this is how it still is in the compiler that we ship today. So this has not been fixed yet, so to speak. So this is, again, the tagged union strategy for the AST nodes. You can see I got a Boolean in there. You can see I got an enum in there. What are the line and column doing? They just keep coming back. Like, I just was so paranoid I was going to forget what the line and column of stuff was, but you can just calculate it lazily. So yeah, once again, stop memoizing stuff. I can calculate that. Right. Also, I was also storing like links to which tokens does this AST node point to and all these things. It's a tree structure, so you only need to store one. That's less of a data-oriented design thing and more of just I realized that I could calculate something. Again, calculate something rather than memoizing it, right? That's what this bullet point is again. And then, okay, the encoding strategy is going to come back now, right? So here we go. I'll put up the new one. The new one is I wrote a little hacky script that ran the whole standard library tests for both cases and just kind of counted up how many of them there were divided by the total. So these numbers are pretty accurate, actually. So this went from 120 bytes to 15.6 average. And it's average because the nodes now take up a different amount of size for each one. So again, this is not what it is exactly. This is optimized to fit on a slide. But it is the encoding strategy. So you can see that there's a main token. All of these are stored with structive arrays. So we're not paying for padding or anything like that. There's a left-hand side and a right-hand side that are repurposed depending on the tag. And the point is that we have multiple encodings. So a variable declaration is encoded in 3 different ways. An if is encoded in 2 different ways. A while is encoded in 2 different ways. And there's just an arbitrary number of these encodings, depending on what heuristically we found we needed to be represented in an efficient way. Okay, so I showed you these two. And I actually did collect some performance stats for this. So did it help? Yes. After I did just these 2 changes, I didn't change anything else yet, and I just measured the difference in just parsing a whole bunch of files. This is the stats that I took. And wall clock time is the big one, right? And if you do 22% faster wall clock time, something that I'm quite happy with. So that's good. But we're not done yet. There's still 3 more stages in the compiler pipeline. So I will talk about this one. I'm low on time, so I won't talk about this one. I won't talk about this one. Suffice to say, the same strategies work. But let's go look at the ZIR one, next phase of the pipeline. So this one's going to take in a syntax tree, and it's going to output an IR that has no type analysis done yet. So here's what we had before. Before we had, it's basically polymorphism, object-oriented programming, that whole thing. So each node will have a different amount of size depending on which one it is. Pointers to talk about each other. One canonical, in this case the tag, it's not the encoding strategy, right? There's one canonical way to represent everything, which is nice in a maintainability perspective, but not as ideal for memory footprint. So here's some observations. Not every instruction needs a source location. Some can be inferred from some other context. Source locations can be U32 indexes into the tokens array or AST node. So that's going to drop the size of that one in half. Let's see. Also this one, before it was like some canonical source location thing. Now, since we're doing encodings, the encoding tells you the meaning of the source location. So that the encoding can say, in this case, the source location is a token index, or in this case, the source location is a node index. And then finally, this is the pointer to index thing, right? So now references to other instructions are half as big, right? So there's that one. And then finally, references can encode simple values. So if you're just talking about, a true, like literally the value true or false, we don't need to create, a whole instruction to represent that. The reference to true or the reference to false itself in the IR format can just have an enum tag dedicated to that. I'm going to just gloss over that because I don't want to run out of time. But anyway, suffice to say, before it was an average of 54.0 bytes each. And sorry, we're going to do one more observation here. We're going to use the encoding strategy. Obviously, that's what I've been keeping saying. So we're going to go from the polymorphism strategy to represent memory to the encoding strategy. So we go from 54 on average to 20.3, again, on average. And download the code if you want at the end and check my work. I did some scripts that just ran against the whole standard library to figure out these averages. So this is the encoding strategy. I had to simplify it a lot to just fit it on the slide, but it's the same deal, right? It's the encoding. So you encode multiple different ways to express everything. Here we can see strong and weak. That's a Boolean flag that's been put into the encoding tag. What else can I point out here? I don't think I need to point anything else out. It's the encoding strategy. It's the same thing I gave you 3 other examples of. We went from 54.0 to 20.3. What I do want to point out though is that each of these improvements, we cut the size of each object in half or smaller through these techniques. Like the amount of memory that this thing is using drastically reduced. And did it work? Like, does using less memory result in less cache misses? Well, empirically, yeah. In this one, it gave me a 39% reduction of wall clock time, which is ridiculous. And that's on top of the other one that I just reported for just doing it for the other 2. I guess I had more of these objects in memory than the other one. So that works. Like in a real world project, it works. If you do the tricks, you will get faster code. And now I know I foreshadowed this embarrassingly parallel thing here. So I had one more thing to report, which is that when I went ahead and I implemented a thread pool, or sorry, King implemented a thread pool, which I just copied from him. Thank you for that. And then I made it distribute the work of doing this embarrassingly parallel part, on the thread pool. And this is on my Dell Inspiron. It's a pretty beefy laptop, right? It's a good laptop. When I did this, just for this part of the pipeline, it came out to 8.9 millions of lines of code per second. So that's pretty fucking fast. And as a bonus, the ZIR, right? The output of this part of the pipeline, it's now only 4 arrays. It's a tag, it's a common data, and then it's like an extra array, and then there's a string table. It's arrays. That's it. It's stupidly easy to save and load that from disk. There's a syscall on POSIX called write-v or read-v, where you actually just give arrays to the OS, and it just does the whole thing at once. Like, it's one syscall to save these to the cache or to load these from the cache. So like this number here, this includes saving the data into the cache, right? Like we're interacting with the file system here to avoid this work next time. Okay, caveat though, right? I'm only talking about this orange part. And these parts of the compiler pipeline are no joke. I know, is that Walter I see there? Yeah, I know you're thinking that right now. So I do want to highlight these areas over here, because that number I gave you, that's going to go down a lot, right? If I can keep it above 1 million, I would love that. But obviously, if these parts of the pipeline are harder, that number is going to go down. That number is just for the orange part. I just want to be perfectly clear. But let me just zoom in and tell you, like, okay, where are we at? Like, what's going on here? So I made this slide so that you can kind of see the idea. The part that I gave you that stat on, that part's done, okay? But we're still working on the back end. So we're at about 35% of the behavior tests are passing for the self-hosted compiler. So every time I've been reporting on these improvements, I'm talking about improvements that have been made in the self-hosted compiler, which is not what you get if you download Zig today. If you download Zig today, you get the slow one. So if you are interested in this and you haven't tried it yet, I actually kind of do recommend waiting. Like, maybe wait till these numbers go up to, like, I don't know, 90 or so. You know, wait till we have a release where we ship this new code as the default and then take it away. So I just wanted to be very frank with the progress report here. And I think let's move on from here. So let's summarize. This is what a computer looks like from a memory perspective. Add CPU cache to your mental model of computers. CPU is fast, memory is slow. Identify where you have a lot of the same thing in memory and make that size of each thing smaller. There's a bunch of handy tricks you can use to reduce the size of things. So indexes instead of pointers. Watch out for type safety. Store booleans out of band. Eliminate padding with structive arrays. Store sparse data in hash maps. Use encodings instead of polymorphism. And you know, as you can see with the Zig compiler, it's worth it. Like, these tricks have actual real benefits. So that's it. That's my talk. Thanks for listening.